So this time we are going to now just talk about the orbitals, right? We promised you in the previous session that we are going to have more information, and whatever we are learning henceforth is getting us closer to doing proper electronic configuration at the SHS level. Now, one thing that we have introduced ourselves to is the orbitals, right? Now, there's a bit of information that we need to know about the orbitals. Let's get deeper in this section. So what did we say orbitals are, right? We said this is how an orbital look like, right? It's in the shell. From the previous session, it's in the shell, and then they are the green boxes. So they are space within the atom, right? And then we said, by definition, an orbital is an area within an atom in which there's a high probability of finding a specified electron, and we stressed on the specified in the previous session. And then another name for orbital is subshell. You see, you have a set and we have subset, right? Subset means that a set in something bigger. So a set in another bigger set. So a child of a set, right? So you have a bigger set. Each child, any other set that is inside can be called a subset of that set. So we say that we have the shell, and inside the shell we have what? Orbitals, right? So the orbitals are found within the shell. So the child of the shell directly, we can call it the subshell. So another name for orbital is subshell, meaning they are under shell. That's what it means. Subshell, under shell. So that's what you can do. So they are inside the shell. So orbitals, another name for it is subshell. Subshell is different from shell. Subshell is the orbital. Okay. Now there are types of atomic orbital. Yes, we talk about orbitals, right? The one we see in the different bodies, but then they also come in various types. So we need to look at that. So for the first type, we have the s orbital. That is it, just s orbital. We call it the s orbital. Then the next one, p orbital. The next one is p orbital. What do you think the next one will be? The d orbital. The d orbital. And at our level in senior high school, we'll stop at the f orbital, right? So s, p, d, f orbitals. These are the types of orbitals that we have. We have the s orbital, the p orbital, the d orbital, and then the f orbital. So speed, or spdf orbital. So spdf orbital. We need to keep that. So what helps me is speed, for instance, right? Speed f. So however you want to put it yourself, but spdf in that order. You have to keep it in that order. S come before p, before d, before f. S, p, d, f orbitals. Now let's take them one by one and look at them, looking at different category, different section. So the s orbital, for each of the orbital, we're going to talk about shape, the direction, and the diagram that we'll be using for each of them. So if we look at the s orbital, for example, this is the shape. So the shape is spherically symmetrical, and this is the diagram you can have here, right? So it's spherically symmetrical. This is the diagram that we have here, right? That's what we have for the. So you have to know the shape. You have to know the direction of this particular orbital. It has no preferred direction. There's no preferred direction. So we talk about the shape. The shape is spherically symmetrical. The direction is, there's no preferred direction. It can go in any direction, all directions at once, because it's sphere. A sphere can turn in any direction. So basically, no preferred direction for a sphere because it's spherically symmetrical. And the diagram that we have is an S. So we just have the box and then you label it as S orbital. This is an S orbital, just one box. Non-degenerate. Non-degenerate means that this is an orbital that is not further divided. Some of the orbitals will be meeting henceforth. Some of them will have division within them, right? Those are degenerate orbitals. But then this one is not having any it's non-degenerate. It just means that it's non-divided. There's no division. So the box is one plain box, one whole box, no further division within it. So non-degenerate orbital. Use that to just understand for now, right? We'll actually explain what degenerate orbitals are in full. But let's look at the next one, which is the p orbital. What's the p orbital? So we have to talk about the shape as well. The shape is a dumbbell shape or pear shape. And this is how it looks like. This is how the pear shape looks like. So dumbbell shape is like two oval objects joined together, right? Yes, so this is it. So we have the middle is twisted within, right? It's something like that. So look like a pear, or you can say a dumbbell shape. so it works for you. And the direction, it has suborbitals. So you see, we talk about orbital, right? If we say suborbital, it means that something within the orbital, right? It's that suborbital that are oriented perpendicular along the x, y, and z axis in space. So that's what we have here. The direction, the suborbitals are oriented in x. So this is the x, this is the y, and this is the z direction in space, right? 3D space, right? The Bose diagram is a degenerate orbital, meaning that it has suborbitals. So you look at this particular one, for example, I said it has further division. It's one whole Bose as a p orbital, right? But then it has divisions 1, 2, 3, 1, 2, 3. It's one whole Bose known as the p orbital, but this p orbital is further divided into sections. So the sections include p, another p, another p. So the first one is px, so along the x direction, right? Because we're talking about the direction. So the px, the py along the y direction, and pz along the z direction. That's why we have these three: ps, py, pz. That works, right? So this is a degenerate orbital, meaning they're an orbital that has further division within it. So that's basically what you need to get. So the s orbital and the p orbital are the most important one you need to know when it comes to the shape, direction, and the Bose diagram. For the d orbital and the f orbital, at our level, we don't go much in deep into that, but then we just need to know something bit about them. So the d orbital is also a degenerate orbital, and then this one is having how many? 1, 2, 3, 4, 5. 5 suborbitals. It has 5 suborbitals. So it has a full d orbital. What is a d orbital? But there are divisions, and there are 5 divisions, 5 smaller houses within it. And each of these smaller houses are called suborbital. We say sub is something we need to suborbital, meaning found within an orbital. Subshell means that it's found within a shell, but suborbital means that it's found within an orbital. So these are small houses found within this whole orbital. So the label is a D1, D2, D3, D4, D5. D1, D2, D3, D4, D5. And this is a whole D orbital. It's a degenerate orbital. And you know why it's a degenerate orbital now. The F orbital as well. So you go to the F orbital, you have degenerate orbital. It's also degenerate orbital. So F, how many sections? You have 7. F1, F2, F3, up to 7, F7, right? So they have suborbitals as well. This is what you have to know about the F orbitals as well. So we have S, P, D. S has what is a non-degenerate orbital. Its orbital is not further divided. You go to the P, you just basically add 2. So from S is having 1, right? If you add 2, you go to P. That 1 plus 2 will give you 3 subsections here. If you add 3 plus 2, you get 5 for the D orbital. If you go to F, 5 plus 2 will give you 7. 7 suborbital. Then you are fine. Okay. Now, you remember we talk about each shell having a number, right? So let's see what happened. So this is an orbital table that I have for you. We are going to link it, the orbitals, to the various shells. So the K shell, we know that it's shell number 1. If it is shell number 1 needs to have only one suborbital, only one orbital. So keep it in mind. If you go to each shell needs to have some number of orbitals. And if it had that number of orbitals, every shell needs to start from S, P, D, F. That always in that order. So when you get to a new shell, you need to start counting the orbital from S, P, D, F, S, P, D to F. So if you're on the first shell K, it is shell number 1, right? So if it's shell number 1, meaning you need to have only one orbital. And the orbital, if you are starting a number of orbitals, we need to start from S. So that's why we are starting from S. So you see that the K is coming with a shell number 1, and it has only one. So the K shell has only the S orbital, right? So that's what we saw by S. Now if you go to L orbital, L shell, the shell L, the shell number is what? 2. Shell number 2. In shell number 2, they need to have what? 2 orbitals. So the 2 orbitals, you have to always start from. On every new shell, you have to start from counting from S, right? So you have S and P. S and P orbital. That's why you have the S and P orbitals on the L shell. Now, if you go to the M, which is shell number 3, meaning we are going to have what? 3 orbitals, right? Shell number 3, so we have 3 orbitals. And on every shell, we need to start from SPD. So it's SPD. Are we fine? Okay. Now, the N shell is shell number 4. So you need to have 4 orbital. So we start from S, P, D, F, S, P, D, F. Now, this is just an extension, right? If you have shell label O, right, is shell number 5, is S, P, D, F, and G is the next one. G will be the next one that we have. But then at our level, we are saying that we are going to majorly stop at F. And we'll tell you from the periodic table why we are stopping at F, right? But right now, this is how the orbital is linked to the shells, right? This is how the orbitals are linked to the shell. Shell number 1, 1 orbital in S. Shell number 2, 2 orbitals. Shell number 2, 2 orbitals is SP. Shell number 3, 3 orbitals, SPD. Shell number 4, 4 orbitals, SPDF. Remember, every shell has its own SP, something like that. So on every shell, you need to start the orbital from S to P to D to whatever. If that shell just end up having only one orbital like the first shell, then you just give it S. But on every shell, you should be able to put at least starting from S. So every shell has what? S, at least the S. Every shell has the S orbital, right? Yeah. So this is how you link the number of the shell or the shell number to the number of orbitals also have. We'll look at quantum numbers that will also add another layer of understanding to this. And right now, we are trying to just establish the relationship for you to have a way of understanding it and keeping it that way, right? Yeah. We are not done. Now we have understood orbitals, right? Orbital, the test of orbitals, right? But the next time is we now need to know something, maybe the principles of filling the electrons or how the electrons are entered in these various orbitals. We are going to look at that in the next section.